Here is part 2, starting with number 5 of the 4A Algebra 2 review for the exponential functions unit. Here we're going to write the growth factors or the decay factor for each situation, and we're going to write it in 2 equivalent expressions. And that basically means there's the exponential way with the exponent to write it, and there's the radical way with a radical. So the growth factor for a specific bacteria is 3/4 per hour, meaning it decreases. It's 3/4. It not gains, but 3/4 of it is left every hour. The growth factor for each quarter hour. So there is a quarter hour in each hour, which means that we want to split this growth factor into 4 sections of time. And because of exponential functions, they'll be timesing by each other. So in order to create 1 hour, we need to take it to the exponent of 1/4, or the equivalent of that would be 3/4, the 4th root of that. Okay, so B, a certain type of cereal increases in price by a factor of 1.01 each week. Show the growth factor for the price of the cereal each day. There are 7 days in a week. So we're going to take 1.01, take that to the 1/7. That'll be the daily factor, or the 7th root of 1.01. And the initial population of a specific population of bacteria. 10 days later, they measure it again to see that it has tripled. What is the growth factor of each day? So after 10 days, so it took 10 days to triple, meaning that that's the every 10 days factor. So in 1 day, it'll go 3 to the 10th, 3 to the 1/10, or the 10th root of 3. And 2 points on a graph are 0,300 and 3,750. They represent the population of bacteria after X amount of days and are marked on a graph. What is the daily growth factor? So here we can see that we know every 3 days that they grow by 750 over 300, which is 2.5. So to find the daily one, we're going to take 2.5 and do to the 1/3, because we're looking at it every 3 days, or the cube root of 2.5. Which, if you plug that into a calculator, it's not the nicest decimal. It goes on forever, so it's not a perfect cube. So you can just keep it like that. Okay, number 6, the graph represents the cost of medical treatment in dollars as a function of time. D, which is in decades since 1978. What's the growth factor for each half decade? Okay, so right here on the graph, it is already measuring a half decade because of that 0.05 for the time value right there. So each half decade is going to be 202.50 divided by the original, which was 150. And that gives me 1.35. So that's for each half decade. So to find each decade, we now want to double this by squaring it, because we would times it by itself. So that gives me 1.8225. And the growth factor per year, I'm going to take this 1.8225. I know there was 10 years in a decade. So this 1.8225 to the 1/10, or 1.8225, the 10th root of that, which you can keep it like that, or that is about 1.061859, which is very rounded. So in the next question, I'm going to keep the expression. Write a function that represents the cost of medical treatment per decade since 1978. And since that is this one, it started out at 150, so C of D. Cost of medical treatment per decade, it started out at 150, and each decade, it's timesing by 1.8225 per decade. So D is the amount of decades. Okay, and number 7, arsenic 74 is used to locate brain tumors. Its half-life is 17 days, meaning that every 17 days it is half of what it was before. You begin with a sample of 90 milligrams. So writing a function that represents the sample after t number of days. So since this is split in 17 days, we are going to take our factor, which is 1/2, and that's going to be split into the number of days divided by 17. So to the t over 17, or that is the same thing as the 17th root of 1/2, or 0.5 to the t power. So after 1 day, plug in 1/17 to your exponent, and you'll get 86.40 milligrams. And then plug in 6 days. And plug in 20 days. Okay. And the reason, I don't know if I explained this before, but it's a half-life, so your decay factor is 1/2 because it's halving every period of time, and then you can split that by doing the root or the exponent rational fraction exponent for the how many days it takes to be a half. And last question with number 8, filling in the table. This represents monthly revenue of a business rising exponentially since it opened an online store. Filling in the table to represent the monthly revenue, and we have some missing spaces. So this is kind of like what was before. We'll take those numbers that we do know and divide them to find that gap. So 90,000 divided by 72,000 is 1.25. Since that was for every third year, or that was on the third year, I'm going to do the cubed root of that. And this one is not a perfect cube. So I'm just going to keep it like that, because now I'm going to make the equation and then use that to fill in the table. Cubed root of 1.25 to the x, or that is 72,000 times 1.25 to the x over 3. And you can use that equation to fill in your table. I got 77,559.65 or 65 cents. And then 90 for the 4th month, 96,949 and 56 cents. So there you go. There is the unit for a review.